We do want to let you know that this talk is sponsored by the Central Virginia node of the Commonwealth Cyber Initiative, the state program establishing Virginia as a global center of excellence in cybersecurity through supporting workforce development and innovation at the intersection of cybersecurity, autonomous systems, and intelligence. Each year, CCI and CVN sponsor research and experimental learning projects. Today's speaker is a recipient of that funding, and we will be hosting Dr. Jayasimha Atulasimha. Our distinguished speaker is from an Engineering Foundation Professor of Mechanical and Nuclear Engineering at VCU College of Engineering. Dr. Atulasimha is an expert in nanomagnetic and spintronic memory and neuromorphic computing devices. As a fellow of ASME and an IEEE Senior Member, he's also the current chair on the TC on Spintronics, IEEE Nanotechnology Council. His impact in the engineering community is profound, and in today's session, he'll delve a bit deeper into the intricacies of quantized transformers for building energy forecasting in smart cities, focusing on cybersecure IoT devices with AI and ML on the edge. Diving into the crucial role of edge computing and emphasizing its real-time processing, economic bandwidth, and privacy benefits. Please enjoy this conversation. And Dr. Atulasimha, I now turn it over to you.
Thank you, Jen, for the kind introduction. I go by Atul, and I'm in the Mechanical Nuclear Engineering department, also with affiliation in electrical and physics at Virginia Commonwealth University. So the title of the talk, which was based on my project, is Quantized Transformers for Building Energy Forecasting, but more specifically or more generally, I will be talking today about AI hardware for cybersecurity. And the reason for this is we have a bunch of projects from CCI, and some of it was also started with NSF, more on actual device side. And the quantized transformer is the current one, so we just have a preliminary slide on that, but we have a lot more information on the past projects, which are kind of more complete now. In terms of the students and collaborators, very specific to the CCI work, this does not include all my students, only those working on CCI projects at some point in time. So Walid, then Shabir, Fahim, and Mahadi, as well as Drithiman. There are various collaborators. We have worked with Manik Group, Hadimani Group, at VCU, and Hoda Group at Virginia Tech. For the more NSF-funded work, which is also presented here, we have collaborations with the Friedman Loop Group at UT Dallas, Quillions at CNRS France, and Kaushik Group in India. So to summarize the lab's work, which is my lab, which is not just the work related to CCI, but to just give a big picture of all the different flavors of research going on in my lab. Historically, early on, I started in magnetism and specifically voltage control of nanoscale magnetism. The idea here is if you have a magnet and you want to rotate the magnetization state, that is, change it from a 0 to a 1 or an off or to an on, this is very useful because once you write that state on or off, you don't need any power and you can keep it forever, for centuries, right? So a lot of these magnetic kind of memory were becoming important in the random access memory of your computer, but it used to cost enormous energy to switch it. So we kind of build these devices which are smaller than the wavelength of light in our lab and show that we can switch these states using electrically generated strain or a direct voltage, and then try to look at using this for various memory device concepts, right? And one of which we are trying to commercialize as well. And then from this interest in non-volatile memory, there was a natural tendency to go into classical AI hardware, where the idea is you have these large neural networks, but at the heart of it is every output of a neuron is multiplied by a synaptic weight. And if we can implement the synapse with some nanoscale device, our interest being nanoscale magnets, then you could store that information forever. The multiplication operation becomes easy, and you can have, in theory, you could come up with networks which are very, very efficient. So this is kind of a leverage point from my basic work to more CCI related work. But as I will explain later, that building these nanoscale devices is more long-term research. So the funding from CCI has helped me transition into what is more short-term, which you can implement as an algorithm or in an FPGA, where you can deliver the results much more quickly, so it's more applied. And we will be talking about that next. My group is also interested in quantum control of spin qubits, but again, this is not something I'm going to talk about today. To summarize my lab's work, which is specifically what we have done with CCI funding or related topics, we have had 4 projects so far. Some are completed, which is why you have more published work there, and some are ongoing. So the first one we had was more on biomedical cybersecurity with the Hadimani group, where we were trying to use AI to predict electrical fields in the brain from a magnetic stimulation. Um, and then we had a project with the Munich group where we were looking at predicting or forecasting the building required energy required in buildings. And the idea here is this is a time series, so you need to predict for months, years, etc. You need a lot of data and you need to train a model, and that's often energy intensive. So we were using CCI to see if there are physical device based approaches where we can predict this long-term behavior. And then the more recent projects, one is what's called anomaly detection at the edge. So if you have anything like a signal that is coming, an aircraft with some flight parameters, by just looking at what parameters you have at this instant of time and maybe the instant back, can you predict if this is in the normal operating mode or there has been an attack on a system? So this is what's called edge anomaly detection. And then the work that we are also working on, which is a little ambitious, so we still don't have results, is this quantized transformers. And transformers are these very complex AI models that are used where you have time series data, etc. And we are trying to, again, use that for cybersecurity applications. So these are the 4 projects. So the way I'll organize my talk is first to go into motivation. Why are we so interested about energy efficiency and hardware resource efficiency? Then we will go about talking about 3 types of projects that we are, broad classifications of projects that we are working on, and summarize and talk about future directions. Now, the most interesting question of why we want to look into these energy efficient hardware solutions for AI is this, that if you look at the cost of a Google search, it's about 1 kilojoules of energy. So in a year with 2 trillion Google searches, just for doing a Google search, this is the amount of energy being spent annually. This is trillions of kilojoules. But instead of just talking about kilojoules, let's look at it in some other way where it's easy to measure. And this is not just AI, this is for all computational tasks or all the energy used by one company alone, Google. In 2019, you can see exceeds the energy utilized in 1 year by many countries of this size, right? So what I'm trying to, and this is an exponentially growing energy requirement. So it's very clear to see that in the future, we are not talking about being energy efficient or green in terms of what energy or carbon emission there is from going from point A to point B by an aircraft, by a car, but what is the energy cost of doing a computation, or doing a Google search, running a program, etc., right? And because this is becoming increasingly important and AI is used in so many applications, it is of interest to actually reduce that energy. And that is the first point here that I make about sustainable computational requirements. And the other thing, which is also becoming equally important, and especially in the context of CCI, is that you would like to do computing at the edge, like in a small chip here, and analyze some data before you transmit it, right? And that edge application has very little power. You're not on a server which has huge amount of energy. You also don't have much hardware resources there. So that is also driving what we are looking at in the edge AI applications. So, but the edge means different things to different applications. It could be a car which is self-driving. In that case, you have a lot more energy and computational power than, let's say, a small implanted biomedical processor, which has less power, very little power, and very little size and hardware resources. But as you can see, these are all the different applications that are coming up on the edge. And of course, energy efficiency is extremely important because you don't have much energy in any edge application, right? And then you also have the benefit that you don't have to communicate to a server because you're trying to process more data as close to the application as possible. This also means low latency. That means you can respond quickly. You don't have to go to a server and come back. And this is the case because inference, that is making those decisions based on pre-trained or learned networks, is something which is very, very much preferred on the edge. And it's also being done. The question is, how do you make that more and more efficient? And there's also more cyber secure, because if you're not communicating with the server, then there are fewer entry points. So these are all the benefits of doing it on the edge. The challenges, of course, are the energy and the limited hardware resources. So with this, I'll go into a little more technical detail of the talks of the research that we have done. We'll start with what is called quantized synaptic weights for various types of deep neural networks. And to give a general introduction, let's first try to understand what a typical deep neural network does, right? So you have inputs. These are the many inputs that you have. Typically, you would take an input from this, let's say input 1, input 2, input 3. You'd take input multiplied by a weight. You take the other input multiplied by a different weight, take the third input and multiply by another weight, and so on. And you would sum all these and give that as the input to the next neuron. So you see that there is a lot of multiplication and addition that goes on that results in what is called matrix multiplication. And a lot of making this efficient is to make the hardware that can do these operations in an efficient way. So typically these weights here are stored at very, very high precision. And there have been a lot of people, and this is just an example, who have been looking at what if we can take this weight and make it less precise, right? Because if I have to store a weight which is very precise, I need to put it in what's called a 16-bit floating point format where it has 16 bits of information. But if instead I want to only store this weight as, let's say, -1, -half, 0, half 1, then it has only 5 states, and I could fit it in 3 bits, right? So I could make that hardware resources almost 1/10 if I'm able to limit this weight or limit the resolution of that weight. That does not be very accurate, right? But then the issue is I could go one step further, and this is more basic long-term NSF funded work, where instead of storing it in a CMOS device, I can have a special not transistor or not CMOS based device, which is low resolution because it has only a few states, but it's also non-volatile in the sense once I store this weight, I have learned or trained my network and I store this weight forever, right? So I don't need any power to keep this weight on. And the question is, as these devices become nanoscale, for example, our simulation here looks at a device which is about 500 nanometers in length and maybe just 50 nanometers in width. And at those scales, what we are trying to do is move what's called the magnetic orientation from this end to this end, where everything is up to a magnetization, which kind of switches, And depending on where that domain wall is placed, the resistance changes. So these devices are incredibly stochastic in the sense that you want to move it to one place, but it doesn't move there. It might sometimes be here. It might sometimes be here. It might sometimes be here. So now not only do you have limited number of states, they are also extremely noisy, right? And the catch here is, or the question that we asked is, can we still use such devices to come up with AI that are very, very accurate in the inferences that they make? And the answer is yes, we will look at that later. So we characterized again the device in terms of its variability and so that we know what to work with. And another interesting area here when it goes to hardware is, can you then take these hardware and do certain applications like multiply and sum so that it is much faster and more energy efficient. So that involves a concept of what's called a crossbar. So rather than talk of a very complicated semiconductor crossbar, let me introduce this idea using a 1903 telephone exchange, which is about an idea or concept 100 years back. So you have many senders here, and then you have receivers here, right? And these are all switch points. So depending on which switch point you choose, you can send from a specific sender to a specific receiver, right? And in modern crossbars, what happens is you can have neurons here. Different neurons give inputs to these lines, which are in the rows. And then at the cross point between this column and this row, I can have this memory device here that then stores a different conductance state. So if I put a voltage, the current that will flow along this line really depends on the conductance state of this device, which I can change. It could be a magnetic device, it could be a resistive device, etc. And therefore, if I simultaneously give inputs from these multiple neurons, the current that flows through this will be a product of the conductance and the voltage that I apply. So I do a multiplication operation and then I add all these currents, right? So you can have some cool concepts like that in hardware, which makes it much faster and more energy efficient to do it. So this is kind of a background. And we very soon realized, and this is again more NSF funded work, where if you're going to work with these weights here, which are extremely low resolution and extremely stochastic, you are not going to get very accurate predictions unless you do something. So you write this weight and then you come up with your final answer. When there's an error, you do what is called a back propagation. That is, how do you change your weights? And you do that back propagation, and this is well known, in very high accuracy, but then you clip it when you retrain these weights, right? So you then retrain these weights or reprogram these weights only if they exceed a certain threshold, so you don't have to write too many weights. And the other thing is, in the next training cycle or pass, you're working with not weights that are accurate, but you're working with very approximate or crappy weights. So over the time, the system learns to work with these weights which are not at all accurate, which are stochastic, and learns around that and gives you good performance. And that is, in essence, a key area of mixing the hardware and the algorithm kind of work that we have been doing here. And what we did is start with a very simple MNIST data set, that is the 0 to 9, the digits 0 to 9, and see if you can recognize them. Again, this is a very simple task. It's like a small undergraduate project if you do it with an existing MATLAB code, but that's not what we're doing. We're asking that if we use all these devices which have very low resolution so that the memory is small, can we still get off with very high accuracies? And so this is the topology of the network. This is the number of neurons in these different layers, input, output, and the hidden layers. And then what we are trying to show here is that we can get very high training accuracy. And what these results mean is, if I had a floating point, like let's say I have a 16 or 32-bit representation for those weights, this is the accuracy that is there in the training and in the testing. Testing is in the prediction with the number of epochs. But let's say at this point, you can see that if I have a two-state device, that is, I can only store zeros or one, then I have a huge loss in accuracy for the same network topology. As I start putting more states, 3 states, and eventually 5 states, I almost reach state-of-the-art accuracy, right? So now I have 3 bits or 5 states, which is giving me accuracy close to having much, much more memory. And so what we proved here is that we can indeed work with these nanoscale devices, which are stochastic and store very few states and still get accuracy. So that is an advance with potential advance in looking at AI hardware that can do things in an energy efficient manner. Right. So with this background, we transferred to a CCI project where we are looking at what's called autoencoder based anomaly detection. And the idea here is if you had a typical neural network, you would have an input here and you would, let's say, have an output here. If you look at this output and I had given the number 1 and it recognizes it as the number 2, I can say, hey, you're not doing the right thing and there is an error, and feedback this error and change the weights. But in these anomaly detection tasks, many times you don't have data that is labeled. You don't have data which is, for example, this is a correct data and this is an anomalous data. So what you do is you run the system with data which is not corrupted or not anomalous, but with the right data, right? The normal working of the system. Then what you're trying to do is reduce the number of parameters that you have to a smaller space. So this network learns in this bottleneck by reducing to the bottleneck layer and reconstructing what was given to it. So you give it something, you reconstruct what you give. So you're training it with purely data which is not anomalous or correct data. And this network now learns the structure of that data, right? So you have never trained it on an anomaly. You only trained it on data for the system that's working well, and it's able to reconstruct this output in the output layer perfectly what you give, right? So now you don't need a labeled data. You're just running the system multiple times and training it. But when you then give erroneous data in, it does not know the structure of that erroneous data, and therefore it's not able to reconstruct it back. And looking at how different this is from the data you give in, you can classify it as whether it is not, it's a normal running or whether there's an anomaly here, right? So this is how these autoencoders learn to extract patterns and representations, and you don't need data that is labeled. You're just training it in an unsupervised manner. But our kind of innovation on this is that these synapses that we have here, we are also quantizing them. So making it very easy to implement on hardware. And we actually tested it against some data to show that you can do good anomaly detection here. So again, the idea here is you give an input, there's an output, you have a reconstruction error, and looking at this, you are able to classify it as data which is not, there's no anomaly or there's an anomaly in the data. I won't go too much into the details. The slides have all the information that is there. Often these data come in packets which have many, many variables, and you need to encode it in what's called a one-hot encoding, which is kind of explained here on this slide, how you're able to convert this to representations. We also have the paper on archive, which was cited earlier under the 4CCI project, so you can take a look at the details. We went one step further because we had that NSF background where we wanted to look at things not just on an FPGA, but whether you could do it with a nanoscale device. So we went ahead and modeled what if these synapses were made with nanoscale devices with all the variability that goes with it. So what we did is we used magnetic parameters. We looked at the stochastic distributions. That is, when you train it, it will not always come here. There may be a spread around it as characterized by this. That will then change the conductance state. And then we implemented all this in a very specific architecture, right? So this is the input and output are 122. The first and the third hidden layer have 32 neurons, and the bottleneck layer has only 10 neurons, right? So that's why you're extracting information into this bottleneck layer that has a very specific pattern. And when it differs from that pattern, of course, you will not be able to reconstruct and detect an anomaly. So at this point, I want to mention there are two things here. So when we mean hardware implementation, you could be looking at a chip that is based on CMOS plus this non-volatile synapses, which is extremely hard to make because it means integrating a CMOS uh, kind of device with a different kind of device. And this is more long-term, right? But from a point of view of CCI, one could demonstrate a similar idea. For example, by multiplying by non-volatile weights, you could just use a lookup table on an FPGA. And that's the short-term kind of goals that we are after, which is more applied, quick transition, or proof of concept demonstration in 1 year and so timeframes through the CCI projects, right? But anyway, to go into the details of this goes into the details of all the clipping algorithm that is used to quantize weights when you train with data, and all the kind of equations involved. But the most important result that we see here is this. If you're looking at the accuracy and your used floating point precision for your synapses, this is what you get with the number of epochs. And for a 5-state quantization, this is what you get. So as you see here, there is some loss because of the quantization. But very importantly, as in the previous case, when you take a real device which has noise associated with it, the noise helps you learn better. And with 5 or a limited number of states, you get almost better accuracy than a floating point, which takes 16 bits instead of 3 bits, for example. And the noise or stochasticity in the device is helping us. So when we do more FPGA kind of implementations, we have to see how to include this noise to help our learning so that we can have a fewer memory states and still get away with very precise predictions or accuracy with which you detect anomalies. The next thing of interest is the following, that if you looked at floating point precision, this is the total number of weights that you had to program, right? But with our quantized 5 states, for example, you can see the number of weights that you're changing or training is 1,000 times less. That again is a lot less energy in training this network, which was an important result. To summarize, we could just use 5-state and get almost state-of-the-art accuracy, and then using the number of training will be extremely small, and this is very easy. This is a very good solution to implement in hardware, right? And in the long run, we could also look at actual nanoscale devices to bring about this synaptic weight, but that's long term. In the short term, we are looking at whether we can just do it using an FPGA for prototyping. And then we are looking at encoder-decoder E-field predictions. This is a separate project. This was, as I mentioned, one of the first projects. So because it was early on, we did not quantize anything here. The idea was, I said, my colleague, Dr. Hadimani, was interested in applying magnetic fields to the brain, and he wanted to predict the electrical fields. This typically takes hours on a computer. So using all the finite elements models they had using the finite element model they had used to go from the MRI of the anatomy of the brain as well as the coil position to the induced fields, we were able to learn this whole thing with a deep neural network and then make these predictions much, much faster. So again, I'm not going to go over the details. These were the various head models that was used. And then these were the coil positions. This was kind of the predicted fields by finite element that we learned. And then you can see here that we were then training the network to predict what the E-field distribution in the brain would be when you gave some magnetic inputs. And this was kind of the architecture of our network, which is what's called an encoder-decoder network. And then we could train it so that the error became smaller over many epochs. And you would see here some of the predicted results versus the ground truth based on the finite element simulations on what we could predict with our networks. So to summarize here, we found a very efficient way of predicting the E-fields in the brain. This was connected to the cybersecurity project because for biomedical devices, this is just exemplary. You can ask the question, what if there is a stronger signal or a malicious signal? Would it produce too high a field, etc.? So it's very good to, you cannot look at some information and say, I'll take 4 hours to compute, right? You need to kind of compute on the fly using this kind of a network, which has been trained on these more complex finite element simulation, but it's much faster in its execution. So with this, I'm going to change topics a little. So all this while I was talking of very traditional neural networks, deep neural networks, and the various applications that we have played around with them. Now I'm going to switch gears and talk with what's called reservoir computing and specifically physical reservoirs. So the idea is in a traditional network, you give an input that produces the something to the next layer, next layer, next layer, etc. Right? But if you have a long time series data, for example, if I speak for an hour, each of what I speak is a data point, right? So if you want to put my 1 hour's data in this, in 1, 2, 3 inputs, this input after some point will blow up. That means it'll have too many inputs, right? So the way I do it is I take a sentence, feed it here, take the next sentence, feed it here, and so on. So I kind of segment this data and send it over time, right? But the problem then is if I put one sentence here and it comes out, I put the next sentence, it comes out, there is no interaction between the sentences. So in order to make that interaction happen, what you do is use what are called recurrent networks, in the sense that you have information at t equal to 0 that comes in here, t equal to 1, t equal to 2, and all this information kind of mix and interact with each other so that you can process information that has correlation with many events in time, right? So the problem with such networks, they're hard to train, hard to implement, etc. So there was this idea of using physical reservoirs. And what the physical reservoir does is you're giving an input to this reservoir at some time, and then that produces a change in this physical entity and in this physical layer, and these kind of talk to each other and form loops. So I could send at some, let's say, time 1, then at time 2, it's here, time 3, it makes a perturbation here, time 4, it makes a perturbation here, at time 5, it may come back here. And so the information I gave at time 0 or time 1 is back here at time 4 or time 5, interacting with the new information I gave you, right? And this kind of interaction and loops are not dictated by you. They are kind of determined by the physics of the reservoir. So if you, in our case, if you have a bunch of magnets, if you perturb one magnet, it'll perturb all the magnets. That perturbation comes back as long as it doesn't get damped out. And you can use those interactions to then process information. So this is, again, nanomagnets that we have built in the lab that could do such reservoir actions. We worked with a group in UT Dallas that came up with this incredibly complex reservoir and simulated and showed that you could do a lot of these tasks, elementary cell automator tasks, with using such reservoirs. We went one step further and asked the question that, look, this is only digital data, right? So this is zeros and ones. But what if we have some analog signal and we want to present it? So the idea we have is we would have what's called a carrier frequency, and we would modulate its amplitude based on what signal we want to send. And then we would send this to some input nanomagnets here, and then this would interact, and then we would pick up the resistance variation from these output magnets or output magnetic tunnel junctions, and then show this is what we get. So this, and then take this, and only the output weights are trained for us to do some kind of identification, for example. And what we show is that we could classify square and sine waves, which is a standard thing. We had this thing, parameters which are called parity check, which shows how nonlinear it is, and short-term memory that shows how much memory there is in the system. And then we could predict a time series, which is called a Mackey glass time series, using this kind of a reservoir. So this is really the task here, is to look at how much these reservoirs, so these are incredibly easy, like low size, low weight, low power, but how complex tasks can they predict? And this is where we worked on a CCI grant here with Milosha's group. And what they had was building energy monitor data, right? So what is the normalized power required for so many hours in a building? And from this data, we were able to train our physical reservoir. Of course, we simulated the physical reservoir, not extracted. We could not extract information yet under this project from an actual nanomagnets resistant state. So we simulated it and trained this network and showed that we can really predict data well, right? And there was also the standard architecture to doing that was using LSTMs that Milosha's group predicted, and we compared the physical reservoir versus this and saw that we did pretty well. So that is one task there in reservoir computing. So the final topic that we are still working on, and it's an interesting topic, is the idea of using transformers. So what transformers does is allow you to process these very large sequences of data. And again, these models are huge, so it's not easy to work with them. And our question is, for some of these layers, can we look at quantizing them so that it makes it more efficient? And this is still work under progress. So with this, to summarize, quantized synapses, we have shown are highly quantized non-volatile synapses. They seem to work wonderfully well, even with the device stochasticity. What we are interested in is, okay, we have looked at some simple deep network, some convolutional networks, some autoencoders, but how scalable would our work be to much more complex models such as transformers, which is being evaluated. We have shown that it is well suited for anomaly detection, image recognition, etc. on edge devices. So we now have the data and the confidence to actually try to implement on something like an FPGA. And it appears that one question we have answered is we can inference. That is, once you've trained this network, it can predict very well, or it can classify very well with very limited resources. But what about learning also from new data using these very low precision hardware? So this is work that we have not yet done. A lot of groups are looking at it. So this would be an interesting forward direction in this quantized synapses area. In reservoir, of course, I showed that in principle, we can do some complex tasks at the edge, but how much can we push that boundary to do more and more complex real world problems at the edge using these devices? That's the future thought for reservoirs. And then, as I mentioned, for the quantized transformers, we have the models ready, but now we are working on data so that we can kind of evaluate it in the future. So to acknowledge some of the more basic research using nanoscale devices and their application to AI hardware was funded by NSF, specifically 2 of more than 10 NSF grants, which were on other topics, but 2 supported this area. And then 4 CCI grants that I specifically mentioned here have all in one way or the other looked at edge AI. And we also have 2 VCU breakthrough grants that have supported some part of this effort. And for the future, there is the CLI funding, which has been recently announced, but we have not, work has not started on it yet, but should start in a couple of weeks, which will also look at some of these applications. And then some of the nanofabrication was done at VCU, VMC, NIST, etc. Thank you, and any questions?
Thank you for that talk. If you have any questions, please go ahead and unmute yourself, and please be sure to turn on your camera as well.
Hi, Jen. I have a question for Atul. You hear me?
Yeah.
Yes,
Okay.
go ahead.
So I was wondering, like, what kind of like practical implications, like, did you have some practical usage of these stuff, or all you worked on the offline data?
So, for example, the anomaly detection was based on data that was got from a database, right? But it was trained offline in the sense this is not data that is coming in real time. But because we show that with these very limited resources, we can train it as well as test it with such high accuracies. What we are planning to do next is an upcoming collaboration with Carl, who is training my student on an FPG on the FPGA, is to kind of port these models that we have onto an FPGA so that you can give inputs in real time and then do the anomaly detection in real time.
Okay. All right.
Right. Now, you can also do it technically using this very complicated CMOS device integrated with non-volatile synapse. But one run, first of all, you have to design your CMOS, you have to tape out, then you have to integrate it with non-CMOS device. So that requires really a huge amount of resources with industry involvement. So that's why that's not the first step. If you have that funding, then of course you can do it. But without that, if you can just use an FPGA to prototype.
All right. All right. Thank you. Yeah.
Again, Dr. Atulasimha, we would like to thank you for your talk today. If anyone has any questions following up, please feel free to reach out to us and we'd be happy to connect you with our speaker. Be sure to tune in next week for the next edition in our speaker series. Thank you, everyone.